But you can, so that's the circular radius 2. So this would be the radius squared. So you haven't done that before. But okay, so how do we get the instantaneous rates of change or the gradient function of something like this? Because this is a circle, so it would have different gradients all along it. But one way to do it is to split it up. So if I go y squared is equal to 4 minus x squared, then y is equal to plus or minus the square root of 4 minus x squared. We've put it in kind of more terminology that we know. The plus would probably be this side of the function, and the minus then would be that side of the function, and combined we would have our answers. So let's just look at how we would derive that and what answer we would get. So the derivative of this, I wrote it like this because I'm going to take one with plus and one with minus, one with plus, one with minus. The derivative of the plus one would be, now if I rewrite this as 4 minus x squared to the power of a half, it might help you. So that's going to be a half 4 minus x squared to the power of minus a half times by negative 2x, yeah? So this is taking the plus side. I'll do the minus side over here. Am I right?
Yeah.
Okay, so thanks. So the 2's are going to cancel, but will be negative. Negative x all over 4 minus...
Is it a 2?
The 2's cancel, I think.
Yeah.
There's 2 here and there's a 2 here. Okay? Now this is what we started with y with, wasn't it? This was y.
Oh.
So we take it as the plus on this side, so that's just y, yeah? So I can rewrite the derivative of x over y, or minus x over y. I know, but that's another way of writing it. I'm showing it there will be a y in the answer. Okay. Now, if I take it with the minus, I'm going to do it over here. So take it with the minus. Do the exact same thing. You're just going to have a negative in front, yeah? So, but this time I'm starting with y being minus this. So the derivative is all the same stuff. This time it's a minus. So we get minus a half 4 minus x squared to the power of minus a half times by minus 2x. It actually equals the same thing. You have a negative where there wasn't a negative, so these two negatives make a positive x, yeah? So we have a positive x over negative what we had over here for minus x squared. But we had defined the function at the start as so it is also, no. Is there not another negative somewhere? What have I made a mistake doing?
Is that not meant to be the answer?
It is meant to be the same answer. X. It's meant to be negative x over positive. Is it?
Because you have negative 4.
No, this is supposed to be negative here. This is supposed to be negative. No, sorry. This, why did I put that negative there? I have no idea. I just put an extra negative in. It wasn't. I am right. So these two negatives cancelled, but because this is positive, it's the opposite sign to this, so I can say it's negative y. So it does give the same answer. So it's the negative of whatever x over y is at that particular point is the gradient. Okay. So there's got to be, that's quite time consuming for a relatively easy function. So is there an easier way of getting this answer? And yes, we use something called implicit differentiation, which uses a lot of times chain rule, but also uses product rule to derive y in general. So if we had y squared, and I said the function is y squared, some function in x squared, what is the derivative? How could I write the derivative of that? If this was the original, what would be the derivative of this, y squared?
2y.
Times by what?
2, the function.
Times by, no. So I'm just going to, if the function was this, what would you do?
It's like 2y.
You write 2, you'd write the function again, and afterwards you'd multiply by the derivative of the function. What's the derivative of y always called?
F dash x.
dy dx. Yeah, or f dash x, but we're using the y terminology. So the derivative of y squared is 2y dy dx for this reason. If it's a function, if we're saying it's a function of x, we're not sure what it is, we're saying in general, it'd be 2 times the function multiplied by its derivative. Now in this case, it's 3x squared, but in general, it is this, which means now we can derive y when it's stuck in the middle of this with this system, with a chain rule type of system. So let's look at x squared plus y squared equal to 4. Let's try and just derive this by looking at it without having to go the two ways. What is the derivative? So we're going to derive this with respect to x. So the correct terminology would be write it something like this. A lot of people just skip writing that and just say, I'm deriving this. Implicitly, they just go straight to this. So what is the derivative of x squared? 2x, correct. What is the derivative of y squared? 2y dy dx, yes. We just did it up here. What's the derivative of 4? 0. Okay, I want to get the derivative equal to. I want to get dy dx equal to. So I can rearrange this equation so I get dy dx equals, the derivative equals. So are you...
X over Y.
Yeah. So I'll slow it down. I subtract 2x over here. If I divide over here by the 2y, and the 2's will cancel each other out, my derivative is negative x over y, which is the same as I got over here.
Nice.
So I can now, if it's the y is a function of x, I can now derive something with x's and y's all together. What do I do? Well, I use implicit differentiation. Every time there's a y, I have to think about, okay, that is a function, so it may have to be multiplied by its derivative. And then I rearrange the function to equal dy dx. So
you're just rearranging
let me,
the derivative.
yes, a little bit, yeah. All right, so let me do some more examples before I get you to do some. Okay, that's the theory behind it. So you will not have to split up the relation into its positive and negative, for example. Some of them you just couldn't split up. The first one I wrote with x cubed or y cubed and y in it, that would have been almost impossible to split up into different functions in just x. Okay, so let's...
You don't get this, right? Like in our data book.
I don't think so. No, it doesn't explicitly say. So there's a bunch here we can do. This one is very similar. Let's just do 1b here. So if we have xy squared, what is its derivative? That's what they're asking. So what is the derivative of this? Well, then I think have to use the product rule. Yes, good noticing. There's something times something here. So the first times the derivative of second, or you can do it the other way around, but I'll do it the first one. X times the derivative of that, which is what? 2y dy dx. Perhaps you want to put in brackets. Plus the second y squared by 1. Are we happy with that?
Yeah.
Okay. Tidy it up as much as we can. And then...
Did we say equals 0?
We can't say equals 0 because it equals nothing at the moment. So in general, we just have to write this one as this. This is as much as we can do, and not equals, plus y squared. If we're looking for a particular point, we can rearrange it equal to 0 or something like that. Like,
what is d over dx? What's the difference between that and dy?
it just says you want to derive it with respect to x, as in y is also a function of x. We just don't know what it is. There is ways of doing it, and we did one where, remember the one on, we flipped it. We actually derived it with respect to y. We treated y like it was the x-axis. Yeah. So it's always we're looking at the x-axis as our what we're deriving against. Okay, so that's it. Just in general, rarely you'll see it written like that. You're much more likely to see it like 2b over here, which I'll do next. I can rub this out maybe. 2b, which is x plus x squared, y plus y cubed equals something, and then I can, at the end of this, because there's an equals here, I can write it as a dy dx equals. Okay, so each bit, maybe you see there's another product rule coming here. Okay, so I derive it bit by bit. X derives to 1 plus, and this is a product rule, as product. Okay, so what is so the first by the derivative of the second will be x squared times the derivative of that. What's the derivative of y now?
Square root y dy dx.
No, dy dx.
Just y. Y.
Just dy dx.
Why is it not y dy dx?
Because you just minus 1, power rule. Y to the 1.
It's y.
The derivative of y to the 1 is 1.
No, it's the
What?
dy dx. Yeah.
So it's
Oh,
just
yeah,
dy
yeah,
dx.
yeah, yeah. Dy dx.
Okay, so the derivative of y is dy dx. Very good. It is it's derivative. Yeah, it's not chain rule anymore because there's no square or anything like that. Plus, okay, don't forget to do the other way around as well, which I almost did. Y times 2xy. We happy with that? That was the derivative of this times that.
Yeah.
Plus, what's the derivative of this?
Of what?
Of y cubed. What's the derivative of y cubed?
3y dy dx.
Almost.
3y squared.
Yes. 3y squared times dy over dx. So treat it like a, yeah, but treat it just as chain rule every time. If there was a function here, you would multiply it down by 3, 2, and then afterwards multiply by the derivative. Equals, well, I got to derive this as well. What's the derivative of 100? 0, yeah.
So that 100 just means nothing.
It means nothing. It doesn't affect the gradient because it would be just a vertical translation of some sort. All right, what do I do next? Yes, rearrange and solve. So I'm going to factor out dy dx out of this and this, so that's left with x squared plus 3y squared equals, and I'm going to subtract these over maybe, minus 2xy minus 1, and then divide by this, and I have my derivative. And that's it. And now if I want to find a derivative at a point, I no longer just sub in for x, I have to sub in for x and y, because both things affect the gradient at that point. The x and the y will affect the gradient at that point.